this defense on the architecture-aware synthesis of Pauli polynomials. So just to specify, so with a Pauli polynomial, we just refer to this like structure in the Stax calculus, which is like essentially like exponentiate weight of like a weighted tensor product of Paulis, and we can describe that as trotterization, and we have like this concept of like gadgets with like different legs. And the whole goal of like my thesis was to provide an architecture-aware synthesis algorithm for those Pauli polynomials, or what we refer as Pauli polynomials. So basically, given you have an architecture and you have like your Pauli polynomial, you want your quantum circuit with like the CNOTs match towards like the architecture constraints. So I'll do now a short detour towards Clifford-Tableaus and the architecture-aware synthesis of Clifford-Tableaus. So the reasoning why we're doing this is essentially we came from like parity maps. So parity maps are n times n matrices in GF2, where we can represent arbitrary CNOT operations on n qubits. And if we have like a CNOT on our quantum circuit, we can just like record it as a row operation modulo 2. And then there exists the recursive Steiner-Gauss algorithm by Arianne, Meijer-van and Alex Kissinger. So what we're doing there is, or what they're doing there is essentially, if we have like a column of our parity map, we compute a Steiner tree on the connectivity graph, and then we just apply CNOT operations to fill that Steiner tree, and then we're emptying it. And in the end, we have like a column that's completely sanitized. Then we just do that for every column, we transpose it, and we just flip the controls and targets. So when we're thinking of Clifford-Tableaus, we can think of them as like 2n times 2n matrices in GF2, and we can represent arbitrary Clifford gates on those. And essentially, those Clifford gates are like a binary enumeration of like the Pauli X, Y, and Z matrices, and we have like n stabilizers and destabilizers, and that like describes every Clifford. And like, yeah, just for completeness, if we have like 1, 0, that will correspond to an X. If we have 1, 1, it will correspond to a Y. If we have 0, 1, it will correspond to a Z. And if we have 0, 0, it will correspond to an I. And we can have also those row additions to apply Clifford gates in a pure Clifford circuit. And then we have like H to swap, or like if we want to apply an H gate to like a qubit, we just swap the X and the Z bases. And we have an S gate, we just like add towards from the X to the Z basis. And there also exists synthesis algorithms. So what people typically do is they rely on those normal forms. So essentially, you just have like one layer of H gates, one layer of CNOT gates, one layer of S gates, one layer of CNOT gates, etc. And if you just execute it that way, you will get like a quantum circuit out of your Clifford-Tableau. There's a paper from Edward van der Berg, who like was more like into sampling random Clifford operators, but he also provided like a way how you can do this with like Gaussian elimination. And the like what we can follow from the fact that we can apply normal forms is that like we can synthesize it with like an asymptotic upper bound of n squared log n. But as far as I know by now, there is no architecture-aware synthesis approach. So that was basically the first task we had. So given a Clifford-Tableau and an architecture, provide me a quantum circuit that's consisting out of Cliffords, such that the CNOT gates are routed. And we adopted here the process from Edward van der Berg. So essentially what we did is you pick like one pivot qubit in your Clifford-Tableau, then you bring the destabilizer basis back to just X, I's, and no other Pauli matrices. Then you remove all of the destabilizer interactions, and then you just continue with the stabilizer the same way, and then you just pick the next qubit and you iterate over and over again. 4.7, the sanitization of Tableau signs, I won't go into that now because like it doesn't require any 2-qubit gates, so it doesn't matter. And like overall, our method will provide us like an asymptotic upper bound of n squared instead of n squared log delta, which would be the optimal upper bound you could achieve for architecture-aware synthesis. And delta is the maximum degree of our connectivity graph. So yeah, for the heuristic choice of the pivot, what we did there is just we looked at the first bit and the second bit of like each qubit, indicating if we have like a Pauli X, Y, or Z. And then we as soon as we have this interaction, we just look it up for the stabilizers and the destabilizers. Then we look like the distance from the interaction towards our qubit, and we sum all of that up. And we want to have like the column with like the fewest interactions as possible. And then we just pick the minimum and we make sure it's non-cutting on our connectivity graph. And then we clean up our destabilizers on that. So what we do there is if we're having a Z, we're just applying an H. So we will be in like we will have an X on that specific qubit. And if we're having like a Y, we're applying an S. So we're adding like ones over here, and we will have like an X on that base. Yeah, just a short note, identity, you cannot convert like a Pauli identity to a Pauli X or Y with a single qubit operation, and 1, 0 is X, so that's desired. Then essentially what we're doing is we're just like taking the idea from the recursive Steiner-Gauss algorithm. So we're filling up the Steiner tree in our tableau because we know the right side here is only zeros. We can just apply CNOT operations on the X basis, or like they won't have an effect on the Z basis for that specific row. So we're just like adding a CNOT here to fill the Steiner tree, and then we're emptying the Steiner tree. And we're done. We're having like sanitized one row into X and then only I's. For the stabilizer, we're just taking every qubit that is not our pivot and converting it essentially to Z. So if we're encountering an X, we'll just apply an H gate and we are at Z. If we're at Y, we're applying an S gate, so we will be at X, and then we're applying an H gate, so we'll be at Z. So for the pivot, we have like the slight caveat that if you're having a destabilizer and a stabilizer, they need to anti-commute. Since our destabilizer is already in the form X and then only I's, the pivot element of our stabilizer has to be either Z or Y. So in case we're Z, we're happy. In case we're Y, we will apply an H gate that will basically just flip our X basis to Z. Then we're applying an S gate, which will cancel the 0 here and won't have an effect on like our destabilizer. And then we're applying an H gate again. So now we're in X and we're in Z. And then for removing the stabilizer interactions, we're doing it one-to-one the same as step 3, just like that we flip the control step and the target step. So what we did there as evaluations is we checked our method on a complete architecture. And what you can basically see is that with respect to like the reference algorithm, which was like the implementation from, or the algorithm from Bravi et al., which is like the standard implementation in Qiskit, that has like a better upper bound. So on a complete architecture, we are a little bit worse than, or we are worse than Bravi et al. But if we're like taking that then to like a specific qubit device, here we took like IBM Brisbane, what you can see is that with respect to like the overhead we require from like the most optimal part, we are actually much smaller than like Bravi or Ewald van der Berg, which we then just routed with, I think, like the standard algorithm in Qiskit, which should be Sabr swap. Yeah, so just to summarize what we did so far, we have now an architecture synthesis algorithm for Clifford-Tableaus. We can reduce the CNOT overhead with that when we're executing it on real quantum hardware. And for Clifford-Tableaus, like architecture synthesis is highly sensible because we actually remove a lot of CNOT-Gates. And now the question is, can we apply this to Pauli Polynomials? And now we have like actually the...
Sorry, can I ask a question?
Yeah.
Yeah. Maybe I missed it, but what architecture are you testing on?
Brisbane.
Okay.
It's like the 127 qubits, and basically what they're doing is like you always have this H form, and then you connect it. Okay. As far as I recall. Yeah.
Right.
Okay. So I answered your, yeah, okay. So, I mean, a Pauli gadget is essentially like this exponential of a weighted tensor product of Paulis. And in the ZX calculus, we can denote it as like this gadget, which I think was first done by Alexander Kautan. And then we can just decompose it into like a set of like H gates and V gates. So that's just like a red spider of like pi divided by 2, as far as I recall. And then we have like this gadget in the center, which is essentially a CNOT ladder and a Z rotation. So where we started from is just we looked at the different legs of like the Pauli gadget, and we just like categorized it into, okay, we can just have X legs, we can just have Z legs, we can have Z and X legs, and we just named them as then like Z phase gadget, X phase gadget, Z X phase gadget. And if we concatenate them, we have like what we refer to as a Pauli polynomial. So we have like the trotterization of an operator. And again, we just categorize that into like Z polynomials. So that's our, like when I just have Z legs here. So here you can apply Graysmith algorithm. And when you have like Z and X legs in there, you have like a ZX polynomial. And you can go on up until something you defined as a Pauli polynomial. I just said that because in the literature, people have different names for it. And the nice thing about the structure is essentially you can propagate Cliffords through that. So those rules, I've seen them first also in the work from Alexander Kauton. So you're just having like a CNOT, and you're just like propagating that CNOT through your gadget, and it will essentially introduce a leg here. If you have like an X leg here, it'll just like go through it. And that is well defined. You can also have it like for H, V, and S gates. You can have it basically for your favorite Clifford gate. And the next nice part about Pauli polynomials is if we have like two gadgets, we can decide that they're like either commuting or not. So they are not commuting if we have an uneven amount of legs or non-equal legs. And if we have like an even amount of legs, we can just like swap them. Yeah, so there already exist synthesis algorithms for Pauli polynomials, but there exists no architecture-aware algorithm. So the question was, hey, can we extend that? And the algorithms we're focused on was like at first PauliOpt. So that was like by Stefano Gogioso and Richie. Then we had like a generic compilation strategy for the unitary coupled cluster ansatz by Alexander Kauton. And then the Steiner-Gray synth, which is like the architecture-aware synthesis of phase polynomials by Arianne, Meijer-van Griend. So for PauliOpt, the whole idea is, I'll just like outline how it works. I have like a more detailed part, especially like on our extension here. Essentially, the idea is, hey, we have like our ZX polynomial in the middle, and then we have like a parity region or CNOT region to the left and to the right. And we'll just use simulated annealing to try to move as many CNOTs as possible through that ZX polynomial, such that if we would implement it on an architecture, the amount of CNOTs you require would be as few as possible. And our idea essentially was, hey, if we have that ZX polynomial, can we just split it in half, like iteratively, and just try to like also optimize subregions. And the nice thing about that is that essentially the parity region to the left is the adjoint of the parity region to the left, to the right is the adjoint to the left. So if one repeats the algorithm over and over again, which you typically do for variational Ansätze, the left and the right will always be the adjoint, i.e. you don't have to implement it on your quantum device. Then for UCCSD set, so the algorithm by Alexander Kauton, the idea was, hey, we're assuming that we can just like reorder our gadgets as we want, because if our angles are small, they are like very, very similar towards commuting, and we won't have that big of a Trotter error. Like the angle, so the alpha. And then we're just like applying graph coloring, or we mapping like the optimization of, hey, give me like a grouping into commuting sets, such that the commuting sets are as large as possible towards graph coloring. And as soon as it's mapped towards graph coloring, we have like those like mutually commuting Pauli polynomials. And then we can diagonalize them into Z polynomials. And we have a Clifford region here. And then for Z polynomials, we can apply Graysmith, and the Clifford regions will just leave them because we're not architecture aware. And the last algorithm, like Steiner-Gray synth, the idea is essentially I have like a Z polynomial that looks like that. I'll just take a qubit with like the most legs. I'll split it into like where I only have legs and where I have no legs. And for the part where you have legs, you take like a neighboring qubit with most interactions on your connectivity graph. So assume like you have Q0 here and Q1 here. Then you're taking a CNOT and you're propagating the CNOT through, and you're just collecting all CNOTs in the end. And then you're just regrouping on your qubit, like, okay, where do you have zeros, where do you have ones, and then you just continue. That overall provides a runtime of m squared q. So m, the number of gadgets, q, the number of qubits. So yeah, I think now we're at the actual synthesis of Pauli polynomials. So you've seen all the algorithms, so polyopt, UCC SDZ, and Steiner-Grayson. For both polyopt and UCC SDZ, it was basically a plug and play, because like for polyopt, we can just say, hey, we have now a Pauli polynomial, we have the CNOT ladder, we can compute the minimal assignment of CNOTs on that CNOT ladder. Pretty straightforward, and like the H and the V gate are just single qubit Cliffords, so we can compute that, and we just store the Clifford operations. We just decided to use CX, CY, and CZ. We can just store them in Clifford-Tableaus to the left and to the right, and with those we can like just estimate the overhead we require. Then we also implemented our optimization strategy. As I said, I won't go into that. It was just like a straightforward like extension of what we already did. Ask me later, please. And for the architecture where UCC SDZ, we're doing like 101 the same thing as we would do for UCC SDZ with like the small caveat. We're taking like the commuting regions and diagonalizing them, and then like we're using Steiner-Grayson, which is architecture aware. And for the Clifford regions, we take our Clifford synthesis algorithm, which is also architecture aware. So again, it's like pretty plug and play. And then for Pauli Steiner-Grayson, so for the extension of Steiner-Grayson to Pauli polynomials, I was like, well, actually, if we're looking at most of algorithms, we are just kind of like splitting them arbitrarily somewhere in the center up to like certain heuristics. But Grayson is so powerful because like we're taking one qubit with like the most like legs present, and then we're splitting it into, do we have like some interactions or do we don't have some interactions? And then we're taking like the next neighbor and we're just trying to remove as much as possible. But the issue with that is, or what I found is I then just like was like, hey, that should work if we're assuming end-to-end commutativity. It didn't, because like we were always like in some sort of endless loop of like one recursion step of mine just introduced a new CNOT or introduced a new leg, and then other just like removed it again. And then my solution to that was kind of greedy, just keep the CNOTs at specific regions, take like those regions and sub-synthesize those. You'll still get like a very, very good splitting that also takes the legs into account, but you could increase the depth. So yeah, as I said, we had then like two recursion steps. The first one was like the identity recursion, and the second one is the Pauli recursion. So it's like one-on-one the same structure as like a Grayson structure. For the identity recursion step, the first part was like, hey, just select a qubit. We took here the heuristic in equation 7. So the whole idea is just count in your columns where you have like the most of like I, X, Y, and Z, and then count the amount of least I, X, Y, and Z, and just take the difference of those. I don't have really a good explanation for that. Like I just tried different heuristics and that worked, or it worked the best. And then if we have that qubit and we have like here on our like polygadget like X, Y, and Z legs, we're just like partitioning in this into like a set where we only have X legs, a Z where we only have a Z where we have only Y legs, a Z where we have only Z legs, and the I legs. So the I legs will just like continue with identity recursion step. For X, Y, and Z, essentially what we're doing is we can easily diagonalize that because we only have X's, so we're applying an H gate, and that will give us like a Z leg. For Y, we're just applying like a V gate, and that will give us like a Z leg. And for Z, we don't have to do anything. Then we'll select a neighboring qubit with like, again, same heuristics. So take the most legs, but don't take them like the smallest one. And then we were we're grouping them into 3 subsets. So at first we have like identity qubits. For that, we just have to like swap all of the legs we have present now into the second subset. The second choice we can have is like we took just like the 2 largest phase gadgets with like the two Pauli legs. So for instance, X and Y or X and Z or Z and Y. And then we just took the remaining in the third set because we have to do something with it. And the nice thing about like, if we're just having like two Pauli legs here, we can easily convert those two Pauli legs into like a Y leg and a Z leg. And if we're having like X and Y, we just apply an H gate. And then if we have like, what we'll basically have is like on the two adjacent qubits, we'll have like either just Z legs or Y and Z legs and only Z legs. So if we're applying a CNOT in this orientation, so control target, we'll remove all of the Z legs in our ith qubit, and the same if we're just applying it here. Then we store those operations for every set. So just make it clear here on that circuit to the left and to the right, and we'll just like further recurse down until we just have like single leg gadgets. We can just convert them into like our X, Y, and Z rotations. Yeah, so when we evaluated our stuff, we were looking essentially at, hey, what are the analytical key difference we have among the approaches? Then we were looking at the trotterization error of like the reordering of gadgets our approaches will provide. And at last, we looked at like how good are we actually at optimizing CNOTs versus like how much do we have like an additional routing overhead. And at last, we were like, hey, how did our algorithms perform on like real molecules? So yeah, the analytical key differences, I just took that table from a master thesis. So SDNC is for synth divide and conquer. It's just like our polyopt implementation. And runtime wise, what you can see is that like our PSGS, so polystandard array synth, is kind of there like just the fastest because we just have like Q and M squared. And this end-to-end commutativity is essentially, do we assume that we have to swap our gadgets or not? And for the UCC-SD set part, we have to assume that because, I mean, we could just take like the regions we have and apply gray synth there, but gray synth is more powerful when you have like longer Z gadgets. And for PSGS, this is kind of baked into our algorithm. So since we cannot choose how we order our gadgets, we were looking at, well, if we're taking them analytically, so we're just computing the matrix exponential analytically and like the unitary of our quantum circuit, how much is the fidelity between those two? And in Alexander Kautan's work, there's like this assumption that all your weights so all your like alphas have to be very, very much smaller than 1. So we just drew here like the line, we multiplied like our Hamiltonian always by just a constant t in like 0 or 2 pi. And then like this line here just provides the portion where like the largest t is greater than 0.01, 0.1. And essentially what you can see is that for UCC-SD set, in that region, we will provide, with respect to the trotter error, a fidelity of 99%. And the next nice thing about it, what we found for those two molecules is that our polystandard array synth algorithm also provides this very, very good trotterization error. And I mean the same for H4. The only, or like the reasoning we had for that was essentially what we're doing is we're providing an alphabetical ordering of like the Pauli terms with respect to a certain qubit permutation. And yeah, like I think there's another paper that like showed that this is quite helpful. Yeah, then
sorry, can I just to interrupt just
sure.
for a question? So this is really a chemical system or chemical Hamiltonian which you're considering here, right?
Yeah.
And what does the P stand for?
Parity encoding.
Okay, not a chemical element.
Yeah, it's like
really H2.
Yeah, it's H2, just like with parity encoding. And please don't ask me what parity encoding is, because I just took them as they were. But
okay, yeah. And H4, like, is this a chain of hydrogen atoms, or
it should be like wait, what is H4?
I mean, it could be a hydrogen chain, but it could also be arranged maybe in a ring or something. But Just asking.
I never thought of that. I always like in my head it was always like CH4. It could be that this is a copy paste error. That's something I actually have to look up in the data. So it's not on my slides.
Oh, you mean it's like, what is it then?
CH4 should be method.
Yeah.
Oh.
Okay. And
Yeah.
do you also know how, okay, I mean, just to understand this a bit better, right? So when you say, so this UCCDS stands for unitary couple cluster, it should probably be singlets, doublets.
Yeah, it's like with singlets and doubles as far as I know.
Okay, it's just
I mean, I just took where I have like those the circuits from is like from the TCAT benchmarking set.
Okay.
Yeah.
Okay.
So yeah.
So okay, so maybe one should probably look it up there. I mean, I'm just wondering because you talk about photo splitting, right? And my first question would be, what is actually the how is the Hamiltonian split, so to say? So what are the different parts of the Hamiltonian, or how is it kind of split to do the trotter decomposition?
I mean, you're always assuming that you have like a Hermitian operator, which is like a weighted sum of tensor products of polys.
Okay.
And then you're exponentiating that. So you're doing like this like molecule simulation. And
okay, yeah.
Then there is, I forgot the name, but there's like one paper. And what they essentially did were they were looking at like, okay, like since I can reorder in the sum, however, like my terms, however I want, and assuming like level 1 trotterization error, what's the best ordering I can get?
Mm-hmm.
And they were like, if you're doing alphabetical ordering, it's not that bad, as far as I recall.
Yeah, right. Yeah. Okay. But I mean, so I guess one would have to go into the, I mean, I guess, yeah, in your case, you didn't really focus on the chemical method of these things, but it was more like you take this as a benchmark circuit and then just try to optimize it.
Yeah.
Okay. Yeah. Okay. Fine.
Okay. So yeah, then with respect to CNOTs, we did like the same as for the Clifford circuits. So we're just generating at this time random Pauli polynomials. And we had like once a complete architecture and once a line circle architecture. And what you can essentially see on the complete architecture is that like our our version of polyopt didn't do or did close to none or like negative optimization. So like this is the reduction in terms of CNOTs. So if I'm reducing more CNOTs, it's better. And if I'm negative, I'm actually introducing CNOTs here. And overall, like the architecture version of UCC set and polystandard gradient worked the best. And when we're like jumping over to a line, what you can see is that like polystandard gradient works overall the best, and that like for the other methods which are non-architecture where we have like still like this, we will introduce a certain amount of CNOT overhead. So since random circuits typically don't like represent the problems we want to compile, we were looking at the molecule dataset from TCAT. And wait, here should be the name. Oh yeah, sorry, Christian, here it is. It's like CH2. Yeah, CH2 should be CH4. Okay, yeah, so no, here, H4. Okay, interesting. Then I don't know the molecule. So essentially, I just took here the Jordan-Wegener and the parity encoding. The Bravi-Kitavec encoding worked the same as the Jordan-Wegener one. And like what you can see is that if we have like more qubits and like with respect to the gadgets and fewer gadgets, the UCC set algorithm works better on a complete architecture. But as soon as we got like further gadgets, the polystandard gradients worked quite well. And what you can also see here is that, I mean, we're still reducing the depth. So like in the brackets, you can see like again, like the CNOT, or in this case, like the depth reduction factor. And like we're still reducing the depth, but we're not reducing it as well as like, for instance, UCC set. And when we're like looking on, I just took here the line architecture. So when we're looking at the line architecture again, we can see that like in this case, like polystandard gradient is actually pretty good at like reducing the CNOT count, apart from like this one example. But again, with the cost of not being that optimal with reducing the depth, which is to be expected because we have like always built CNOT ladders, which like just naturally are created by our recursion structure. So yeah, the whole architecture-aware extension of UCC SDZ is possible. The strategy of polyop like works well on ZX polynomials. We've already seen that. But like actually, when we like extended to Pauli polynomials, we saw little to no effect. Then the Poly-Steiner-Grayson algorithm is actually highly performant on architectures, but again, we suffer from like this not increase of depth, but not as good reduction in depth. And then Poly-Steiner-Grayson provides like this better trotterization error because essentially we have like this alphabetical ordering with like permutated polyterms. And conclusion and future work parts. So I'm just going to repeat myself again, but we have like this architecture-aware synthesis algorithm for Clifford-Tableaus. We have provided those 3 architecture-aware synthesis methods for Pauli polynomials. And the question now is, or like PSGS performed like especially well for larger molecules. So future work-wise, what would be nice is to see an n squared log n or n squared log delta, with delta the largest degree of your connectivity graph bound for Clifford-Tableaus. It would be nice to add the diagonalization process you have for your UCC SDZ, at least like for single qubits and paired qubits, into like the Poly-Steiner-Grayson algorithm. That might actually help because you're looking like then at like one pair, which is like completely Z or X or Y, just only Z, sorry. And the last part is try polyop with like arbitrary 2 Cliffords. That would actually be something I would be interested in because it could improve the performance of it a little bit further. Yeah, so I'm in the end of my talk. So yeah.
Thank you.
Thank you very much, David. So Christian, do you want to be chairing right now? Like I don't know what's suitable.
Sorry.
Yeah, I mean, for me it's also fine if you continue sharing. I mean, no problem. I mean,
okay, so I'll just yeah.
Since I already asked some questions, so yeah, just maybe someone else also has some more other questions.
Yeah. All right. Yeah. Is there anyone else that has some questions?
I see a hand from yeah.
Hi, David.
Hello.
Congrats on this amazing work. I have a question about this trotterization method that was used for benchmarking. May I ask, when you do this, are you trying to verify the like the circuit that you synthesized is exactly the one that you try to find, or you are benchmarking for noises?
You're talking about like this part here?
Yeah.
We were actually just using the precise matrix exponential of like our weighted sum of tensor products of Pauli, so like of our weighted Hamiltonian, and then we're taking like the unitary of the quantum circuit we had in the end. And like in my tests, I was always for that reordering recording, like in which order the gadgets are in the end synthesized, and I applied that permutation towards like the level 1 trotterization, then compared with that. So it was just like on how large is the trotter error with respect to compilation.
I see.
Yeah.
So have you thought about, so this is basically just comparing the fidelity of your quantum states after being acted on by your synthesized circuit, right?
Yes. Yeah.
Okay.
And I mean, the issue was with like real devices. If we would have taken like one of the 12 qubit and 640 gadgets, I think I tried that once with like the IBM simulators, and I had like a fidelity of 1 percentile in the end, like because you still have like your noisy circuits, you still have your operations, so it was not really comparable in that sense.
I see. Well, that's very interesting because in our project, we are also doing the routing problem, but we account for the noises. And we discovered that when you don't deal with the noises, like when you don't deal with the coupling noises, the fidelity is very low. But as soon as you take into account like the difficulty of coupling 2 qubits, or T1, T2 errors, by using the calibration table provided by IBM, the fidelity was significantly improved.
Interesting. So basically you were routing like with respect to the graph, but like weighted with like, do you have certain, okay.
And the other thing I'm very curious about is when we try to calculate fidelity beyond 12, it blows up because you're dealing with 2 to the power of 12 times 2 to the power of 12 matrices.
Wait, which like that's why I took like the smaller molecules. So that's why I took H4 and H2.
Oh, so you also encountered the same issue when you calculated fidelity?
I mean, you mean with respect to operators?
Yeah.
Yeah, obviously, because like you have like 2 to the power of like let's say 12 times 2 to the power of 12 a matrix in your memory, it won't last.
Oh, I see. Okay, thank you.
I mean, have you tried the Hellinger fidelity on like?
But you're still dealing with like 2 to the power of n entries, right? It's just like you don't deal with a matrix, but you still have a vector that is of that dimension. So I don't think that would save the problem.
Yeah, okay. Yeah, I see that issue. I never thought of that.
Christian,
Actually.
You wanna go ahead with the question? See your hand is raised.
Yeah, sure. Sorry. Christian?
I'm muted, yes, right. This is more like a follow-up on the question by Sarah as well. So, okay, so first of all, I guess what you're referring to in the last point was you could, of course, try to use a state vector simulator, so you don't really have to actually store the whole Hamiltonian or the unitary time evolution operator as a matrix. But then, on the other hand, it might not be. I mean, okay, it depends a bit what the fidelity refers to. Is this just the fidelity of the quantum state or of the whole time evolution operator?
Yeah.
So I mean, it's the fidelity of the whole unitary, so to say.
I mean, yeah, for me, it was more like, hey, I need like one similarity measurement and I'll just go with. And I think in this case, it's like the operator, like of the actual density matrix. But like, I think Hellinger fidelity is just like with respect to the counts.
Yeah, okay.
Yeah.
And so I was also, okay, so just to understand this graph a bit better, right? So it seems like the fidelity is actually quite low, right? And also, you would expect that the photo splitting would be more precise, but I guess the
core assumption behind it is you want to keep like your parameterizations of your like of those alpha zeros and alpha ones like way much below 0. And if you're having them way below 0, and that's basically behind this line, so in between like 0 and 0.1 for the like largest interaction, your fidelity is up to like 99%.
Okay, but would this mean just for a single time step or for the whole time trajectory?
No, like you're not doing Hamiltonian simulation. That would be the fidelity over Hamiltonian simulation. You're trying to find the ground state of a molecule, as far as I understood it.
Okay. Because I was assuming, yeah. Okay. Now I get the point. So basically, you use this as a unitary coupled class or something to. Yeah. Okay. You want to find the ground state, but then why is there a time parameter? This.
I just needed to like because like for parity there were like already inserted just I don't know like random parameters, and I just needed to show well, if we're scaling up t, how large can we scale it up? So I just took the parameters that I found in t, multiplied them by like this time t in this case, and then just looked at the fidelity. So so it's just a question. Yeah, but like essentially what you could argue for is that you could argue in this case that your parameters can be up to like pi divided by 4 or something, and you still preserve like a larger fidelity than UCCSD said.
Okay, that's the point. So the time t is not really your physical time, so to say, of the physical system, but more like the internal parameter which you can choose, and then you would just choose it in such a way that your fidelity is still very large, so to say, right?
Yeah. And like the whole argument behind it was like you cannot like influence how PSGS swaps gadgets. So you don't want to like start here because that would be quite bad.
Okay, yeah, thank you.
Yeah.
So if I can ask a follow-up question on this slide as well. I was a bit confused about it because I was assuming that your routing strategy takes in a circuit specified in some manner, say as a sequence of Pauli exponentials, and then just finds a way to route it, but implements the same unitary. But this slide seems to imply that you are moving stuff around in a way that is not preserving the semantics of the circuit.
Yeah, that's precisely this end-to-end commutativity. So do I assume that I can, like that I'm coming from molecule simulation and I can swap my tensor products of polys anywhere how I want? And the point is, like, for polyop, you don't. For UCCSD pair, you also don't. But for those three algorithms, you have to, kind of.
I see.
Or you taking that assumption?
Did you also look at circuits that come from like logic circuits, say that are compiled down from like a Toffoli-Hadamard type gate set, where you would also have some Pauli exponentials, but
actually no.
Phases? Okay.
Like I was always assuming like this whole molecule structure because like it provides you like with like this nice interface. And the question, that's also like, because essentially you could convert any circuits into like this exponential weighted sum of tensor products of polys. And the only issue is like, if you would use those methods, you would have like a certain Trotter error with respect to your gates when you would compile it down. So this is super specialized for molecules in this case, or in general operators.
So are your methods not suitable for like exact things like logic circuits?
If you're taking this assumption, you will have like a certain error with respect to your final fidelity. And if your rotations of your if your Z rotations of like your specific gates are large, like obviously you will have like a low trotterization error.
Yeah. In a like a regular logic circuit, I'm thinking of like a Clifford-Tableaus circuit. Your phases will be large, then your error will be massive. If you start moving stuff around, it will be like low fidelity.
Pi to the 4. Yeah. Okay. Yeah. Like could be fine, but that's something I don't have data I can answer.
Yeah. And I had a different question. So you have there's one method which is sort of extending Griend to work with Pauli gadget instead of just the phase gadgets.
Yeah, that's
is it like a really like a generalization? Like as soon as you have only phase gadgets, like Z phase gadgets, it just becomes Griend? Is it like a generalization in this sense, or does it do something else?
Not really, because you're not propagating CNOTs all the way to the end. That was essentially what I tried to outline with this slide. Essentially, we are just like having like larger CNOT letters, and we're just trying to like move them around. The naming convention just came from I tried to extend Steiner Grayson, and I just like threw Pauli at the beginning. Like you can name it different, by the way.
All right. Any other questions from the audience? All right, Sarah, go ahead.
Yep.
May I ask about the Clifford-Tableaus synthesis that you mentioned earlier?
Sure.
So you mentioned that the reason you're using this molecule setting is because they have an easier representation. Is it because you're representing everything as e to the power of minus it phi, where phi is a rotation angle?
Yes.
Oh.
I'm like exponentiating the whole thing.
I see. Actually, when you showed us that picture, it reminds me of Daniel Lintinsky's paper, A Game of Surface Code, where he represents all unitaries in terms of Pauli product rotations. So I think if you want to fill the gap between the circuit model and this molecule simulation, I think you can use that translation to do that.
Yeah, it could be, but I'm not 100% sure about the paper.
Oh, so basically the idea is you already have this recipe to deal with Pauli product rotations, right?
Yep.
You know how to decompose it using CNOT and other Cliffords. But how do you go from Toffoli-Hadamard circuit into Pauli product rotation? This gap is not clear. But I think Daniel Lintinsky answered this question it is just like one table on page 3.
It could be okay, do you have like a link or like just my Keith just asked in the chat for a link, but like is he essentially just taking like Clifford gates propagating through like the circuit, and as soon as you hit a T gate, you just convert it towards like this our Z or our X rotations. And then you just like can build like this gadget. Is that kind of the idea? Sorry, you're muted.
Oh, sorry. So he represents all gates in terms of Pauli product rotations. And then whenever you want to, so let's say you have P and P prime and they commute, then the corresponding Pauli product rotations also commute. You can just verify it linear algebraically. And if they anti-commute, then when you push through it, you keep this unchanged, but then you change this to minus I P P P prime. And then you continuously updated this pi over 8 rotations and keep the Clifford part unchanged. So this allows you to group your Clifford component into one block and a non-Clifford component, which is an analog of a T-gate, into another block.
Okay, yeah. Yeah. I mean, the only issue is then if you synthesize the non-Clifford block, you just have to assume like a shape like this again. And then the question is, does this all commute with like all the other gadgets you have?
Yeah, this may I understand that the first component you have alpha 0, alpha 1, alpha 2, they are the T component of your
like I mean that was just an arbitrary like circuit I just took, but I mean it could be that alpha 1 is not commute, or alpha 1 is actually not commuting with alpha 3, right? So you have to ensure.
Oh, then you can just push through it. You push through it, and then and then you updated your Pauli product.
Okay, yeah. I mean, I'm not sure if you can extend like then Graysynth towards that, because like Graysynth is always about regrouping. So if you have like legs always here, or let's say it's like alpha 3 in front of alpha 0, you would have to commute them through. So you would have to assume this error, because like you just can't push through that. That's the whole idea. Like I'm just taking a subset of them, having like legs, and then I just like decompose them further.
Right.
That's kind of like, yeah.
I think I need to read more into this part of your paper to understand the technical details.
Yeah, I can send you like my master thesis if you're interested.
Okay, thank you.
Okay, perfect. Yeah, no worries.
And we can bring this offline.
Yep. Yep.
I would have also had like a more general question. So, I mean, maybe it's a bit naive, but could it also work when you have, let's say, a partial CNOT-gate, let's say, right? Like what I mean is like, in quantum circuits or in digital quantum computers, implementing a CNOT is typically expensive, so to say, right? Of course. But you could also have a version or some circuit hardware which can implement something like square root of CNOT, or let's say, like a gate which is equivalent to a square root of that gate. So in some sense, if you regard CNOT as a rotation, you could say instead of doing the full rotation, I just rotate by a fraction of the full angle. So I was just wondering, could these algorithms which you develop maybe also be used in such a situation in some sense to optimize the partial CNOT gates?
Are partial CNOT gates Cliffords? Because essentially the core the core idea is where is it here? You can derive all of like this propagation rules for all Clifford gates. But as soon as you had a T gate, for instance, here, it won't work anymore.
Okay, so it might actually, already stop here, so to say, right? I mean, of course, if you have like a product of two square root CNOT gates, it would again be a CNOT gate, but but then okay.
The question is square root CNOT a Clifford or not? And I don't know from my head.
Yeah, probably not. But I think you also mentioned this in your outlook, right? In principle, could also generalize the algorithms to more general gates, like more general Clifford gates, besides CNOT, right?
Yeah, that was the whole idea with like Pauli update. You're not just taking like I just took CX, CY, and CZ because I don't know, I was like, hey, I'll just take those. And it would be nice to have it like for all possible 2-qubit Cliffords, which are essentially then again, like on a logical level, a sequence of H, S, and CNOT gates. Yeah.
Yeah, okay. Yeah, Keith also just wrote the same thing in the chat, right? It's not partial synod, this Clifford.
Yep.
Sorry, if anyone wants to ask questions, please interrupt me. Sorry for asking so many questions.
No, it's fine, don't worry.
Could you go to like the page where you have this all-to-all connectivity in the slides?
You mean this one here?
Yeah, so would
Yeah.
you mind commenting on, when we are doing routing, we noticed that the underlying graph connectivity has a good impact or like a big impact on the routing strategy. Have you discovered or observed
Oh, no.
something
End-to-end commutativity refers to the poly gadgets. So can I swap them vertically or not? I should have like possibly named it like swapping or something. Like can I just swap them arbitrarily? Do I assume I have to swap them arbitrarily or not?
Oh, so you are not assuming all-to-all connectivity.
No. I'm always like the core idea is always like give me an architecture and this Pauli polynomial structure. I'll give you like a quantum circuit that can run on that specific architecture graph.
And you just use one architecture to do the benchmark?
Depends on the problem. Like here, I took, I think, a line and a circle architecture. And here I also took a line architecture. For the Cliffords, we always took the IBM quantum computing, like the IBM architectures for various qubit sizes.
I see. So when you perform on this line architecture, did you notice anything when you have to, like, in terms of routing, like what costs you, like, do you have any observation with this structure?
You mean, I mean, in general, if you're optimizing for a specific architecture, you typically are better than if you would just route it. Like if you would optimize it and then route it.
What do you mean by optimizing it?
Like first you have like your standard circuit optimization algorithm. So for instance, UCC SDZ, and then you're applying, like in this case, it was like the TCAT routing algorithm, the standard TCAT routing algorithm. And what you can see, if you're counting the number of CNOTs, the number of CNOTs here is larger than if you would just use like one of the architecture-aware ones.
Oh, interesting.
Which is, I mean, it's also, it depends on your problem setting and like on the specific algorithm, obviously. But yeah.
So you are saying that the current state-of-art compilers, such as TCAT, are giving a better strategy than the routing strategy proposed? Am I understanding this correctly?
They're like the amount of CNOTs is larger when we just run it with TCAT, and it's smaller when we run it with like the Grayson detection or like the architecture-aware version of it.
And this the number of CNOT directly affect the fidelity that you calculated at the end?
Yes, but it's hard to verify because that's why I said earlier, when you try to like run it like on problems where you can actually see that you have like a huge difference, you're already having like what is this, like 700 CNOTs on like an 8-qubit circuit, which will give you like a final fidelity of not much, like a few, like just like a small portion. Like at least I experienced that like once. I didn't use like an 8-qubit real device. I used like just like a noise model from IBM. But again, like I was like at 1 percentile, that's where I stopped. If you're looking into, that's a little bit of a different context. If you're looking into our Clifford synthesis paper, we did something similar there. So we just used the Bravi algorithm, if you remember. So we used like here the algorithm by Bravi et al. and the like the standard algorithm, like in our algorithm and in a complete architecture, you have like this huge gap, which comes from like we just don't have the perfect bound in terms of CNOT-Gates. And if you route it on a specific architecture, you like need way fewer CNOTs. And I haven't shown that, but wait, that's somewhere in my backup slides. Yeah, essentially what we did, we took like Quito and Nairobi. And what you can see is that in most of experiments, like the fidelity of our algorithm was typically higher than just using like routing. And you can see that especially on Nairobi. So the execution time is lower because you have to execute fewer gates. And again, like the fidelity was like a little bit higher, except from like a few parts where actually Qiskit found a better circuit.
Hmm.
So like since CNOT is very expensive to calculate and like it affects your fidelity a lot, it makes more sense to optimize it. And by routing, you're always like placing swap gates. So you're introducing more CNOTs to fit to a specific architecture than the one you assumed in your optimization algorithm.
I see. So, well, I agree that based on the Google paper, we can focus on the count of CNOT to reduce the error. But sometimes you have some edges that are very expensive. But you know, it's possible that you have to walk through that edges so many times. Like you seem to have kind of reduced the number of CNOTs in your overall calculation, but you compromise the CNOT errors actually accumulated in this process.
You could, for instance, just take instead of a graph, a weighted graph.
Yeah.
Yeah. I mean, since you're like at the base of it, okay, for PSGS, I'm not 100% sure, but at least for that algorithm, you can definitely, because like you have the Clifford synthesis, and the Clifford synthesis is just based on you're computing a minimal Steiner tree. You can do that for weighted graphs, as far as I know, so you could extend that in that way.
Okay.
And then it would be interesting to see if it's actually, yeah.
Yeah, I'll link the paper in the chat.
Yeah, sure. That would be cool.
All right, so we've been going for close to an hour now. I don't know if there is a like a limit to this type of defense thing, or if you can just keep going. I think yeah, don't know if there's any questions left to be asked as well.
Can I ask about the lower bound that you showed just now? The Clifford lower bound.
The lower bound.
Oh, like so you have this n square over log n.
That would be the best upper bound you could get for Gaussian elimination in terms of steps. Wait, right. I have it somewhere here. Yeah. You mean this one?
Yes.
Yeah.
So we know that for CNOT circuit we have this, but once you add the Hadamard and ASK gate into the circuit, can you still get this bound?
Yep, because like essentially you can assume like one of those like layered forms, and in that layered form you always have like a CNOT circuit, and you can just synthesize that CNOT circuit, and that's just an S gate and an H gate. So in terms of CNOTs, you'll still have that lower bound. Does that make sense?
Sorry, say that again.
You essentially have like that pure CNOT circuit as one layer in like your layered approach from like, let's say, Arianne Gottesman.
Yes.
And you can just store all of these CNOT operations as like row additions modulo 2 in your like parity map. And then you just apply like the algorithm from, sorry, I'm bad with names. But you apply then the algorithm that assumes like the n squared log delta part here. And that would give you like the lower bound. Huh?
Tell Markov-Hayes, or do you mean a specific version meant
but that's n, that's not delta.
Yeah, that's log n. And now the question is, like you can also apply the architecture-aware algorithm, like for every of these pure CNOT layers. And then you're still, since they are finite, you're still bound in n squared log delta.
Delta is the maximum degree of all of the vertices in your graph?
Yes, as far as I remember.
Yeah. Okay, so you get this bound from the layered approach of your Clifford normal form.
Yeah, it should be possible. And like this whole process, I mean, it's also not in the n squared log n because we're not selecting like regions. So, I mean, essentially how you would get the n squared log n is like you're selecting like m columns, then you're just like removing all of the duplicates, and then you're like for CNOTs, and then you're just like effectively remove like then you effectively remove each of the rows, as far as I recall. And we're not doing that. We're just selecting one pivot, removing it, selecting the next pivot, removing it. This was more like the first naive implementation.
Oh, okay. Thank you.
Thank you.
All right. Well, if there's no more questions, or Christian, you wanna?
No, I think it's fine from my side. Yeah. Yeah. Thanks for the nice presentation, David.
Thank you all for listening.